Top 10 worthless rocks that surprise geologists. Some rocks sparkle, others end up in museum vaults, auction houses, or private collections worth millions of dollars. And then there are the ones that don't. The rocks no one cared about. They were kicked aside in mining fields, mistaken for construction rubble, or buried under layers of mislabeling in field reports. To most, they were just debris. But over time, geologists began to notice something, a strange consistency in what had been dismissed. Inside these forgotten specimens were things no one expected: fossilized ecosystems, evidence of ancient lightning, markers of meteorite impacts, even snapshots of Earth's deep interior. Rocks that looked like nothing turned out to be everything. This is a countdown of stones that science once ignored, and now can't afford to forget. These are the worthless rocks that surprised even the experts. Don't forget to press and hold that like button, leave a comment, and hit subscribe before we begin. Ranked 10th, bauxite, the rock that was dismissed, then redefined the metal age. For much of its early history, bauxite was labeled as waste. Its appearance, reddish, crumbly, and dull, led many to assume it was nothing more than degraded clay or oxidized soil. In mining regions, it was routinely discarded, unfit even for use as fill. Few saw a reason to study it closely. Its texture lacked structure, and under the microscope, it offered little mineralogical clarity. It wasn't rare, it didn't shimmer, and it didn't command any value on the open market. Geologists were slow to reconsider it. Part of the hesitation came from its ambiguity. Bauxite is not a single mineral, but a mixture of aluminum hydroxides formed through intense tropical weathering. The process, known as lateritization, strips silica and concentrates aluminum in the residual rock. This transformation occurs only under particular climatic conditions, over long geological timescales, in regions such as northern Australia, Guinea, and Brazil. What surprised geologists wasn't just the nature of its formation, but the scale of what they had overlooked. With the invention of the Bayer process in the late 19th century, a method for extracting aluminum from bauxite, this once dismissed rock became the world's primary source of one of its most important industrial metals. Aluminum, once so scarce that it was more valuable than gold, is now indispensable in aerospace, power transmission, packaging, and infrastructure. Over 90% of global aluminum production begins with bauxite, the same material that was once shoveled aside without a second thought. Bauxite was never hidden. It lay exposed in large deposits on multiple continents. What made it worthless wasn't its geology. It was how it was perceived. The scientific shift wasn't triggered by its beauty or its rarity, but by a change in what humans were able to do with it. The surprise wasn't in the rock itself. It was in the realization that one of the most transformative resources of the modern era had gone ignored for generations. Ranked 9th, limonite, the iron stain that pointed to gold. Limonite has long occupied a strange space in geology, too common to attract attention, too vague to classify with precision. It doesn't sparkle, fracture cleanly, or reveal any obvious internal structure. In many field surveys, it has been treated as background noise, a yellow-brown smear on outcrops, or a crust of oxidized material along fractures. It was widely considered a product of surface weathering, a residue rather than a rock, and for decades its presence signaled nothing more than the natural breakdown of iron-bearing minerals, such as pyrite or magnetite. However, what geologists once dismissed as low-grade rust would eventually lead to a reconsideration of how mineral indicators were interpreted. Limonite, as it turns out, is not a single mineral, but a field term for a group of hydrated iron oxides, including goethite, lepidocrosite, and jarosite. These compounds often form in the oxidized zones of ore deposits, where chemical weathering interacts with sulfides and other primary minerals. Because of this, limonite accumulations can become diagnostic, a visible marker of what's hidden deeper below. What surprised geologists wasn't limonite itself, but where it kept showing up. In numerous gold-rich districts across Australia, Nevada, and West Africa, limonite zones were found to lie directly above or adjacent to valuable deposits. In some cases, Areas previously dismissed as barren were re-evaluated based on the reappearance of iron oxide crusts, which had been previously labeled as irrelevant. Soil geochemistry programs began targeting limonite as a proxy for oxidized gold systems. In laterite environments, it also became critical in nickel exploration, where limonite-rich horizons overlaid deeper saprolitic ore zones. Outside of mineral exploration, limonite has also gained relevance in environmental geology. Its ability to immobilize heavy metals and mitigate acid mine drainage has made it essential in reclamation science, a role few would have predicted based on its appearance in the field. Limonite rarely commands attention and is seldom featured in gem catalogs or rock shops. But for geologists who know what to look for, its presence can reshape a map, reroute a drilling program, or revive a mine once thought exhausted. The surprise isn't that limonite exists, it's that it was visible the entire time and still got overlooked. Ranked 8th. Iron slag, meteorite fragments. The trash heap that came from space. In mining sites, smelting pits, and archaeological ruins worldwide, iron slag is a common find, porous, metallic, brittle, and often discarded as industrial debris. For centuries it was understood as the waste product of metalworking. Leftover material from ancient furnaces, the unwanted remains of iron extraction. Its texture is irregular, its surface is dull. Most of it contains no residual value. In surveys, slag is often cataloged but rarely investigated. It is the byproduct of human industry, and by all appearances, that's all it was ever meant to be. But in rare cases, slag-like rocks discovered near ancient sites have revealed something entirely unexpected. Some of these materials, once categorized as artificial refuse, were later identified as meteorite fragments, rich in nickel and extraterrestrial iron. The confusion stems from their appearance. Iron meteorites that have undergone oxidation and weathering can resemble slag in both structure and density. Without detailed chemical analysis, the two are nearly indistinguishable in the field. The most striking examples have emerged from regions like Egypt, Siberia, and North America, where fragments initially dismissed as slag were reclassified after geochemical studies confirmed elevated concentrations of nickel-iron alloys and cosmic isotopes. In archaeological contexts, these findings have forced a re-evaluation of early metallurgy. In some cases, tools and beads once believed to be forged from terrestrial ore were hammered from meteorite iron, making them the oldest known use of metal by humans, predating the Iron Age. Even in the modern era, slag-like materials recovered in desert environments or polar regions have turned out to be parts of undetected meteorite falls. For geologists and planetary scientists, these discoveries serve as a reminder that extraterrestrial materials don't always arrive in clean, dramatic fashion. Some fall unnoticed, break apart, and settle in the landscape, slowly corroding, blending into the debris of human activity. What made these fragments worthless was not their origin, but the assumptions made about them. In a pile of slag, no one expects to find material from outside Earth's atmosphere, and yet in more than one instance, that's exactly what they saw. Ranked 7th. Petrified wood. The fossil forest that was mistaken for stone. Scattered across deserts, riverbeds, and canyon floors lie fragments of what appear to be stone, fractured, heavy, and stripped of any trace of organic life. At a glance, they resemble pieces of eroded rock, often ignored or misidentified as debris from ancient lava flows or sedimentary rubble. For decades, petrified wood was rarely examined outside of paleobotanical circles. Its true nature was easy to miss, and for many surveyors and miners, it was simply more useless rock beneath their feet. But what looked like stone was once alive. Petrified wood is the fossilized remnant of trees that lived tens of millions of years ago, sometimes hundreds of millions, preserved not through compression or carbonization, but through a process known as permineralization. After a tree falls, if it is quickly buried under volcanic ash or sediment and deprived of oxygen, groundwater rich in dissolved minerals can seep in. Over thousands of years, the organic matter decays and is slowly replaced with silica, calcite, pyrite, or opal. The result is a structure that retains the cell walls, grain, and growth rings of wood, but is entirely mineral in composition. What surprised geologists wasn't that wood could fossilize. That much was already known. The shock stemmed from the level of detail that could be preserved, as well as from the environments in which it was found. Entire petrified forests have been uncovered in places as geologically unlikely as Arizona's Painted Desert, Argentina's Patagonia, and Turkey's Gökçeada Island. In some of these sites, the trees lie precisely where they once stood, their root systems still anchored in soil that hasn't supported vegetation for millions of years. Others were carried by ancient floods and buried en masse, offering windows into prehistoric climate events. Even more unexpectedly, the mineral composition of petrified wood varies dramatically by location, revealing the geochemistry of vanished ecosystems. In some cases, the replacement minerals form microscopic crystals that preserve cellular structures invisible to the naked eye, but invaluable to scientists reconstructing ancient plant life. These specimens have helped define eras, clarify extinction timelines, and refine our understanding of prehistoric atmospheric conditions. What was once dismissed as an unremarkable rock has proven to be a biological archive, a record not just of life, but of time, chemistry, and transformation. The surprise wasn't in its existence, but in its precision. For those who overlooked it, petrified wood was just another stone. For those who studied it, it became a chronicle in crystal. Ranked sixth, flint, the stone that sparked more than fire. Flint rarely draws attention in the modern world. Found in scattered nodules embedded within chalk or limestone formations, it often resembles lumps of dull gray or brown stone with irregular glassy fractures. In most environments, it blends into the landscape, mistaken for slag, dismissed as rubble, or passed over entirely in the search for metallic ores. To the untrained eye, it appears to offer no obvious value. But Flint's story is not about commercial worth. Its significance lies in how early geologists underestimated its role in shaping human history. Geologically, flint is a microcrystalline form of quartz, primarily composed of silicon dioxide. It forms through diagenesis, the chemical and physical changes that occur in sediments after burial, often replacing the calcium carbonate in marine shells with silica sourced from the remains of radiolarians and sponges. Over millions of years, this silica slowly accumulates into dense, conchoidally fracturing masses, often hidden inside white chalk beds. While its appearance is modest, its internal structure makes it uniquely capable of being fractured into sharp-edged tools. It was this property that early geologists, trained to seek economic metals and large-scale mineral deposits, largely overlooked. Yet archaeologists found the evidence unmistakable. Long before metallurgy, flint was being knapped into cutting edges, scrapers, and projectile points by hominin species stretching back over 2 million years. From Moldovan tools in East Africa to Clovis points in North America, flint appears across nearly every known early civilization. In many regions, entire trade networks were built around it. Quarries like Grimes Graves in England and Rijkholt in the Netherlands reveal systematic extraction and standardized tool production dating back to the Neolithic period. What surprised the scientific community wasn't just how widespread flint use was, but how long it endured. Even after the advent of bronze and iron, flint continued to be used for ceremonial blades, fire-starting tools, and precise surgical instruments. Its edge, when properly struck, can be sharper than steel. In some cultures, it remained in practical use well into the 19th century, particularly in flintlock firearms. Flint's initial dismissal came from judging it by appearance alone. It lacked shine, color, and density. It could not be smelted, polished, or sold by weight. But beneath that rough exterior was a rock that gave early humans control over fire, food, and warfare. And with them, the foundation of civilization itself. Ranked fifth, coprolite, the fossil waste that rewrote ancient ecosystems. In fieldwork, certain finds are met with indifference or even discomfort. Coprolite is one of them. Hardened, fractured, and often misshapen, it resembles nothing more than a chunk of eroded stone or decomposed mineral debris. In early excavations, it was misidentified, dismissed, or outright discarded. Many believed it to be worthless. the fossilized remains of biological waste with no scientific relevance. For decades, it went largely unstudied. That changed when paleontologists began examining it under a microscope. Coprolite, by definition, is fossilized excrement, the mineralized remains of animal dung preserved over millions of years. Unlike other fossils which capture the structure or bones, coprolites retain chemical and organic signatures, including undigested plant matter, muscle fibers, bone fragments, parasites, and pollen grains. In some cases, these specimens preserve DNA traces, making them a rare and invaluable record of diet, ecosystem structure, and predator-prey relationships. The surprise for geologists wasn't the existence of coprolite, it was its specificity. In deposits from the Mesozoic to the Ice Age, researchers began linking coprolites to specific species based on trace contents and context. Some were identified as belonging to marine reptiles, while others were identified as ancient carnivorous mammals. In caves, they helped reconstruct the seasonal movement of megafauna. In riverbeds, they mapped feeding behavior across long-extinct ecosystems. More recently, coprolites have gained relevance beyond academic science. Their mineral composition, especially those rich in phosphates, has made them a subject of interest in soil science and fertilizer research. In rare instances, fragments of well-preserved coprolite have even entered the perfume industry, valued for their complex organic fixatives similar to ambergris. However, this remains extremely limited and scientific in scope, rather than commercial. The initial disregard for coprolite came from a narrow understanding of what mattered in the fossil record. Bones were prized, shells were cataloged, teeth were measured, but waste, it was ignored. And yet time and science would prove that few materials offer a more intimate, data-rich glimpse into the behavior of long-extinct animals. What had once been considered irrelevant, or even embarrassing, became a key to reconstructing life itself, from the inside out. Ranked fourth, Septarian nodule, the mudstone that split open history. To anyone unfamiliar with sedimentary geology, a septarian nodule might not register at all. Found in dry lake beds, desert basins, and eroded hillsides, these rounded rocks look like cracked balls of hardened mud. Uneven, matte, and unimpressive. Their exteriors are dusty, chalk-like, and easy to overlook. For decades, many were left uncollected, mistaken for weathered limestone or soil concretions with no real use. But when one breaks open, the picture changes entirely. Inside, septarian nodules reveal complex systems of mineral-filled cracks, typically composed of calcite, aragonite, barite, or siderite. The pattern is angular, geometric, and often striking in symmetry. These formations are not random. They are the result of chemical shrinkage and fracturing that occurred as the original mudstone dried and contracted, likely during the late Cretaceous period. Mineral-rich water later infiltrated these cracks and crystallized over time, creating a sharp contrast between the dull outer shell and the vibrant, crystal-lined interior. What surprised geologists wasn't simply the appearance, but the conditions that created them, and what they preserved. In some cases, septarian nodules have been found to contain early fossil remnants, including leaf imprints, shell fragments, or microbial mats, which were trapped within the original sediment. Because the nodule acts as a sealed environment, the contents inside remain protected from surface weathering for tens of millions of years. More remarkably, these formations helped refine understanding of diagenesis, the transformation of sediment into rock. The interaction of organic decay, mineral replacement, and fluid pressure in the formation of septarian nodules provided rare physical evidence of post-depositional geochemistry. For researchers studying paleo-environmental conditions, these rocks provide a window into the chemical state of ancient lakes and marine beds, including temperature fluctuations, water acidity, and the emergence of early microbial life. Originally cast aside as misshapen mudstone, septarian nodules are now curated in university collections, studied in petroleum geology for reservoir analogs, and valued in earth science education for their clear record of internal transformation. What was once judged entirely by surface appearance turned out to be a geologic archive, not of what was seen, but of what formed in silence, under pressure, and over deep time. Ranked third, Fulgurite, the glass tube that began as lightning. In arid deserts, on beaches, and sometimes in forest clearings, slender hollow tubes of gray or pale brown glass lie buried just beneath the surface. Most are no wider than a finger, brittle to the touch, and often broken or twisted in form. They are easily mistaken for melted debris, burnt roots, or even artificial waste. For years, field surveys recorded them as anomalies, and to most geologists, they carried little importance. Their size, inconsistency, and irregular shape gave no immediate reason for deeper study, but their origin tells a different story. Fulgurites form when lightning strikes the ground with enough energy to fuse quartz-rich sand, soil, or rock into glass. Temperatures in the plasma channel of a lightning bolt can exceed 30,000 degrees Celsius, hotter than the surface of the sun. When this energy is discharged into silica-rich material, it melts instantly, following the path of least resistance and branching out in all directions. These root-like tunnels rapidly cool and solidify into natural glass. The result is not just rare, it's geological evidence of an atmospheric event. For geologists, fulgurites became significant not for their visual impact, but for what they preserved. A frozen record of lightning interacting with Earth's surface, including pressure signatures, trace gases, and in some cases, microscopic inclusions that captured the chemical conditions of the air and soil at the time of formation. The surprise came when researchers began identifying fulgurites in ancient sediments, some dating back hundreds of thousands of years, suggesting that lightning events had been shaping surface mineralogy in subtle ways long before modern climate models accounted for it. Even more unexpectedly, fulgurites have been studied as analogs for glassy structures on other planetary bodies, particularly Mars, where similar high-energy interactions may have occurred from meteor impacts or electrical discharges. The misconception surrounding fulgurites lies in their fragility and irregularity. They look like accidental fusions of sand, not something produced by one of nature's most violent forces. Yet within them lies information about planetary weather, high-energy physics, and even potential life markers in extraterrestrial exploration. What was once overlooked as a fused root or shapeless slag turned out to be the crystallized fingerprint of a single lightning strike, a moment when atmosphere, energy, and Earth converged in silence. Ranked second, tektite, the black glass that fell from nowhere. Across Southeast Asia, Central Europe, and parts of North America, small, dark, glassy stones have been found scattered in riverbeds, farmlands, and eroded hillsides. Shiny but pitted, lightweight but solid, they were often mistaken for volcanic debris, artificial slag, or even broken obsidian. For decades, they were ignored by geologists and misidentified in mineral collections. Their presence in unrelated landscapes, with no obvious volcanic source nearby, only added to the confusion. These objects are known as tektites, and their origin is neither volcanic nor artificial. Tektites form during high-energy meteorite impacts. When an asteroid strikes Earth with sufficient force, surface rocks are instantly vaporized and ejected into the upper atmosphere. Some of this material melts mid-air, then cools and solidifies as it falls back to Earth, forming natural glass droplets. Their aerodynamic shapes, chemical composition, and surface textures preserve evidence of violent impact conditions, often dating back hundreds of thousands to millions of years. What surprised geologists wasn't just the process, but how far these glass fragments had traveled. The largest tektite field on Earth, the Australasian strewn field, covers more than 10 million square kilometers, yet the impact crater that caused it has never been conclusively identified. Some of these tektites landed thousands of kilometers from the point of origin, making them physical evidence of one of the most wide-reaching impact events in the planet's recent geological history. Tektites challenged early assumptions about what natural glass could be. They lacked a crystal structure, didn't occur near volcanoes, and showed no signs of metamorphism. For years, their extraterrestrial origin was debated. Only after chemical and isotopic analysis revealed their connection to terrestrial crust, fused, launched, and returned, did their role become clear. They are the result of Earth being struck, violently and without warning. Even now, tektites are used in impact geology to calibrate models of ejecta behavior, atmospheric reentry, and heat transfer. Some contain high-pressure minerals that form only under shock conditions, providing insight into events that are too fast and too hot to observe directly. Others are studied for their age, used to date impact layers across continents, and connect extinction events with physical evidence. The mistake wasn't in finding them, it was in misreading what they were. These black glass fragments didn't rise from lava or fall from human activity. They were created in seconds, launched into space, and returned as silent records of planetary trauma. What once looked like slag turned out to be a signature from Earth's collision with the cosmos. In first place, kimberlite, the cracked rock that carried the deepest secret. There are rocks so unspectacular that they're paved over. Kimberlite is one of them. It weathers to dull greenish gray, breaks unevenly, and spreads in irregular, fractured pipes through ancient cratons. For generations it was overlooked, mapped as intrusive residue, misfiled as igneous debris, or covered by infrastructure. It bore no metal, no oil, no visible mineral worth extracting. In many regions, it was treated as a nuisance to be blasted through on the way to something else. But kimberlite did not come from the surface. It came from the deep mantle. Formed at depths exceeding 150 kilometers, kimberlite magmas rise with extreme speed and force, propelled by high concentrations of carbon dioxide and water vapor. Unlike other volcanic materials, they ascend in narrow vertical pipes, fracturing the crust as they go. And under the right conditions that occur only in ancient, stable cratonic shields, they carry something else with them: diamonds. What shocked geologists wasn't just that kimberlite could transport diamonds to the surface. It did so faster than any other known magma on Earth, in events lasting hours, not millennia. The speed preserved the diamonds, the chemistry stabilized them, and the rarity of the conditions made such occurrences vanishingly rare. Even among thousands of mapped kimberlite pipes, only a few dozen are diamondiferous. The rest remain barren, the geological equivalent of a false lead. The initial misjudgment came from habit. In mining, value is often tied to appearance: veins of gold, clusters of crystal, gleaming ore bodies. Kimberlite offered none of that. Yet within its matrix lay material older than most crust. Xenoliths from the lithospheric mantle, preserved snapshots of the Earth's interior. It became not only the world's only known natural conveyor of diamonds, but also a core reference for understanding the composition, temperature, and evolution of the Earth's deep interior. In places like South Africa, Siberia, and northern Canada, entire industries were built not because kimberlite looked valuable, but because science eventually revealed its capabilities. Its surface was misleading. Its true significance was structural, chemical, and deeply hidden. Of all the rocks once considered worthless, none challenged geologists more profoundly than kimberlite. What looked like fractured volcanic rubble turned out to be a rare intersection of time, pressure, chemistry, and motion. A rock born in silence, risen in violence, and carrying one of the most coveted materials ever found. They were never valuable. They didn't shine. They didn't weigh much. And in most cases, they weren't even named. But as science progressed, so did the questions we asked. What else had we missed? What data was still hiding in plain sight? These rocks weren't just misjudged. A whole generation of scientists had underestimated them. And in each one, the surprise wasn't about the money, it was about the discovery. Because when the surface tells you nothing, what's underneath can change everything. If you've made it this far, you know, geology isn't just what we see, it's what we're still learning to recognize. Let us know which one resonates with you in the comments, and don't forget to like and subscribe to our channel for more content like this.